Okay, in the first two videos in the series on molecular substances, I've described the basic idea that in these substances the forces of attractions happen between molecules. And now what I want to do is start getting into this in more detail. The model system that we're using is we're comparing the properties of carbon tetrachloride, which is a nonpolar substance, with water, which is a polar substance. And the point being that these two substances differ in their properties. All right. And just let me scroll this so we have something to look at here. So the carbon tetrachloride is nonpolar, and the water is polar. Now, what I want to do is start getting into essentially the nitty-gritty of what we call intermolecular bonds or intermolecular forces, and these two terms are used interchangeably. And basically, both of these terms, whether we're talking about IFs or IBs, are a reference to the forces of attraction, all right, between molecules. All right, so between molecules. Now, to get into this, what I want to do is establish some criteria for these kinds of forces, because these forces are hugely important to, literally billions and trillions of different kinds of molecular substances that we know about on our planet, and more compounds are being produced all the time. The reason that this is important is the physical properties of these particles are differentiate how these things operate in our physical world. All right, and just to remind the viewer, for example, the boiling point of carbon tetrachloride is around 76 degrees centigrade approximately, and water is around 100. All right, so these two things differ substantially in their boiling point. Their melting points are also very different. Carbon tet's around -20, and water's around 0. So what I want to do is start talking about the criteria that really differentiates how these the physical properties or the intermolecular forces, the forces of attraction between the molecules. All right. The first issue that defines the strength of the force of attraction between molecules is the structure of the molecule itself. So it's important that the viewer is able to draw, for example, simple Lewis formulas of particles, because for example, in the case of the carbon tetrachloride in the water, it would be almost impossible to see the difference between these particles if you want, for example, to visualize how they operate between two charged plates. If you're not able to draw the Lewis formula, which allows you to get a handle actually on what the structure looks like. The next thing is to be able to evaluate the polarity of the molecule. In order to do that, first you got to have the structure. In order to determine the polarity, you need to be able to evaluate the electronegativity differences between atoms. So I'm going to abbreviate that here, electronegativity differences. And these are the differences in the bond polarity within the molecule. All right, the idea being of being able to establish whether or not there are going to be opposite charges on opposite ends of the molecule. All right, and that goes back to the idea, all right, we're going to take this molecule, we're going to put it between two oppositely charged plates. Does the thing line up in the plates, between the plates? And carbon tetrachloride, for example, is going to have random orientations between oppositely charged plates, whereas your water molecule is going to be lined up in a fixed manner because there's opposite charges on opposite ends of the molecule. Whereas on this molecule, you do not have opposite charges on opposite ends. It's a symmetrical molecule regarding its charges. So this thing has random orientation between oppositely charged plates. Water molecule does not have random orientations. That's what makes water polar and the carbon tetrachloride nonpolar. And then the third thing is molar mass. All right? The bigger the molecule, all right, the more electrons we have, also the bigger the volume. All right, so in this case, especially when we're dealing with nonpolar molecules like carbon tetrachloride, the size of the molecule is going to play a much bigger part in the strength of its forces between itself and the other molecules that are around it. Because the larger the molecule, the more electrons you have, the larger the volume of that molecule, which provides more volume for the electrons to move around. And the importance of that is because when you have a charged particle like an electron and it can move, it can cause the molecule to polarize. So let's see, I'm going to write that in here in a different color. So, and we'll do it this way: electron movement causes instant polarity. Instant polarity. Now, as you might expect, polarity caused by the movement of electrons is weak. So I think I'm going to add that here too. This is weak polarity, right? Weak polarity. So we have three main factors that control the strength of the force of attraction between molecules. So these things control, these three factors control strength of the intermolecular bond, or the IF, the strength of the IF. The structure of the molecule, like in the case of water, we have a top and a bottom. Oops. We have a top and we have a bottom. Then correlating with that, in terms of number two, we have opposite charges that end up on opposite ends of the molecule. And then lastly, but far less important for a molecule like water, we have the issue of total numbers of electrons and the volume that they're able to move around in. This is an issue that is more important for nonpolar molecules than it is for polar molecules. Keep in mind that water on its own merit has got electrons in it, and those electrons can move around, and they can contribute to the polarity of this molecule. In the case of carbon tetrachloride, it's much bigger. Remember from the previous video, it's about 8.5 times bigger by comparison to water. 8.5 times heavier than water. And why that matters to carbon tet is it has a larger volume for electron movement. And that's going to enhance its ability to bond with itself and with other molecules which are equally nonpolar.